class, ladies and gentlemen. We are from the Hong Kong Chinese Women's Club College. Our team number is 61415. To start with, I would like to say something about how we come up with this idea of finding the best position for locating lifts in a shopping mall. One day, as we were trying to find some books in the Central Library of Hong Kong, we found that the positions of the lifts were not very good, and we had to walk long distances to reach them. Therefore, we had this idea. This is the situation of our problem. A shopping mall can be divided into different regions with different numbers of people, but there are only limited numbers of lifts. So our aim is to find the best positions for installing lifts, such that the total walking distances for the people to reach the lift can be minimized. These are the assumptions we have made in our project.
The project is in the shape of a rectangular block, and since it is a rectangular block, all different levels are identical, and for each level, the shopping mall is divided into different square regions. When we are doing our study, we place each level onto an XY plane, and it is assumed that people in this shopping mall can only walk along XY direction. We start with the simpler case in which the shopping mall is a one-dimensional one and there is one lift to be installed. In this figure, the squares represent the one-dimensional shopping mall, and AK is the number of people in region K. Therefore, A1 is the number of people in region 1, A2 is the number of people in region 2, and so on. To find the best position for the lift, first we consider the extreme case. We put the lift in region 1. Then, if we shift the lift to right for 1 unit, the average distances between people in region 2 to region N decreases by 1, while that between people in region 1 increases by 1. And this is the decrease in total walking distance. For each shifting, the total walking distance decreases by this amount. And so it is obviously that when this equation holds, further shifting will not decrease the total walking distance, but the opposite. Therefore, we can conclude that the best position for the lift is the position that divides the number of people into 2 equal halves with 1 half on each side. Then we consider the case 2-dimensional shopping mall with 1 lift to be installed. First, we put the shopping mall onto an XY plane and let X lot, Y lot be the location of the lift. Then a person at the position XY, Y1 has to walk a distance of this to reach the lift. Note that the walking distance along X direction is independent of the Y coordinates of the position of the lift, and the walking distance along Y direction is independent of the X coordinates of the position of the lift. Therefore, the total walking distances along X and Y direction are independent of each other, and so we can find the minimum for each independently in order to find the minimum for the total. This is how we do it. First, we consider each row of the shopping mall as a whole and find the total number of people in each row. Then, by the previous discussion on the case 1-dimensional shopping mall with 1 lift to be installed, we can find a row number such that it divides the number of people into 2 equal halves with 1 half above and 1 half below. And that's the ideal row number for the position of the lift. We do the same thing for the columns. And then we can find the ideal column number for the lift. And therefore, combining these two, we can find the ideal position for the lift. Then we consider a case in which the shopping mall is a 3-dimensional one, and there is 1 lift to be installed. The method we use to find the ideal position is, first we add up the numbers of people in each level with the same row number and column number. Then we can get a 2-dimensional shopping mall. And by the previous discussion on the case 2-dimensional shopping mall with 1 lift to be installed, we can find the ideal position for the lift. After studying cases with 1 lift only, we consider the case in which the shopping mall is a 1-dimensional one and there are 2 lifts to be installed. From the previous discussion on the case 1-dimensional shopping mall with 1 lift to be installed, we know that the best positions of lifts should equalize the number of people on both sides. And in fact, in a shopping mall, it is natural that people will choose the lift which is closest to them. In this figure, the orange stroke cuts the mall into blue and red regions. Blue stroke is the best location of the lift in the blue region, and red stroke is the best location of the lift in red region. D1 is the distance between the blue stroke and the orange stroke, and D2 is the distance between the orange stroke and the red stroke. Since blue stroke and red stroke are in ideal positions, they equalize the number of people in each region. An ideal case exists if we can make D1 equals to D2. To prove its existence, first we consider the extreme case with the orange line on the leftmost position of the shopping mall. Then D1 becomes 0 and D2 attains maximum. Then we shift the orange line rightwards to the rightmost position of the shopping mall. D1 attains maximum and D2 becomes 0. When we shift the orange stroke from the leftmost position to the rightmost position, D1 increases from 0 to its maximum, while D2 decreases from its maximum to 0. There must be at least a position at which D1 equals to D2, and that's the ideal position for the orange line. Based on the existence, we have written a Pascal program for finding the ideal positions for two lifts in a one-dimensional shopping mall, and the algorithm we use in our program is similar to the proof that is shifting of orange stroke. In this figure, the rectangular block is a shopping mall, and the red and blue squares are the positions of the lifts. There are n-1 orange strokes here in this. In this shopping mall, there are m lifts to be installed. Orange strokes are the middle positions between two consecutive lifts, and they divide the shopping mall into m regions. In each region, people will use the lift there only. And blue and red squares are at the ideal positions of the lifts, and they divide the number of people into two equal parts in a region. In fact, what we have done in our project is not just applicable for finding the best location for lift in a shopping mall. It is also suitable for finding the best positions for information center in a museum, or choosing the best sites of building a library in a town. And in fact, it is most suitable for finding the best location for emergency exits and staircases, so that in a commercial building, so that in case accidents happen, people can be evacuated most efficiently. We did not stop our work after our project, and we kept on searching related information, and we found that there has been similar thing done by other mathematicians and they use calculus as the method for finding the ideal position for lifts, and same conclusion was drawn for, we reached the same conclusion for the case one lift in one-dimensional shopping mall with different methods. These are our references, and that's all for my presentation. Thank you.